Ethers are generally unreactive, and that's why we find that they were good solvents for Grignard reagents. There are a few reactions, though, where we can react the ether and form it into something else. One of the more common ones is acidic cleavage, where we break apart the ether into its component R groups. So let's look at diethyl ether. If we react that with a strong acid, we need HBr. In this case, HCl is not strong enough. We need excess of that. We'll show you why in a second. And we need quite a bit of heat. Eventually, we will be able to form two ethyl bromides and water. So the first thing that happens is that we protonate the ether with our strong acid. And this is why we need a very strong acid, because a weaker acid isn't going to protonate the ether. Ethers are not very good bases. But now you'll notice that we have a decent leaving group, actually. We have ethanol as a leaving group, and I have Br- as my counter ion. I could draw an SN2 style reaction, which results in ethanol being formed and ethyl bromide. And in the presence of extra HBr, our ethanol will get protonated, just like the ether did. And you see now again we have a good leaving group that I can draw an SN2 style reaction, and that brings me to the product. So I'm able to break apart this ether and end up with two alkyl halides. The key idea here is that both of these, and if I want to break apart the ether and end up with two alkyl halides, both of these carbons need to be probably primary. They need to be unhindered and able to receive a nucleophile in an SN2 style reaction. If we did this ether, let's say we had phenyl ethyl ether, and we reacted it with excess HBr, our products would be phenol and ethyl bromide. Why might that be? Well, the first step happens the same as what I showed you in the mechanism a few seconds ago. Whereas if we protonate phenol, we might say, well, why can't we just take Br- and draw this arrow push and do an SN2? The reason is that this is a sp2 hybridized carbon. It is not a good substrate for SN2. Remember that SN2 requires backside attack, so basically the bromine would have to come in behind the CO bond, and that would be basically within that ring. So within the ring, where there's a lot of electrons and some steric bulk from the other side of the ring, our bromine would have to go straight at the backside of that CO bond, and that's not going to be possible. So what we're going to end up with is one alcohol and one alkyl halide. So keep that in mind. This is a classic question. Predict the product. And a lot of students will automatically just draw the bromide on the phenyl ring. And now I hope I've convinced you that that is not going to happen. So we're only going to get half of what we expect to with this acidic cleavage because of the type of carbon that one of our R groups has. Another reaction that ethers undergo, and it's kind of an unfortunate one, is auto-oxidation. Say you have a really old can of ether, like diethyl ether, that has sat around for many years. Chances are it has reacted with the oxygen in the air. And oxygen molecules actually spend a good portion of their time in this diradical formation. And this hydrogen here next to the oxygen can actually make a stabilized radical. I'm not going to get into the mechanism here because we didn't necessarily study the radical chapter earlier in the textbook. But suffice it to say, I could create a radical here and we can stabilize that radical. Radical mechanisms are drawn with single-headed arrows. So I could draw this, which would create a radical on the oxygen. And that's going to stabilize this radical, this single electron. Eventually, this single electron would react with another O2 to form this compound. We call that a hydroperoxide. And these are actually solids. So if you are rotovapping some ether in the laboratory and you suddenly see a solid that you didn't expect to have, it may be this hydroperoxide, which is very explosive, very unstable, explosive. So there have been lab accidents where researchers have gotten injured from these old bottles of ether. So the part of the stockroom's job is to test ether and tetrahydrofuran and other versions of other types of ethers for the presence of peroxides. And there are ways to destroy the peroxide before it gets to unsafe levels. Basically, we want to know if this reaction is happening. This is an undesirable reaction that could happen in a bottle of ether. We want to know if it's happening, and we can take steps to reduce or eliminate this hydroperoxide then and dispose of the ether in a safe manner.